In today's lesson, we're going to look at two different sections and two parts of those sections, section 7.2a and 7.3a. We're going to focus on multiplying and adding radical expressions today. But before we do that, we'd like to kind of start off with a little bit of review as we review from Algebra 1. And remembering, when we're multiplying two radicals together, first of all, those radicals must have the same index, and that index is that little number inside the square root in that little hook part of the square root. They must have that same square root in order to multiply them together. Notice when you multiply them together, the little index or root does not change. So here in our first little mini example, we have the square root of 3, remembering there is an invisible 2 there times the square root of 12. We don't write that invisible 2, it's just assumed. So we have the square root of 3 times the square root of 12. That is allowed to be done since they have the same index. So that's the square root of 36, and obviously that is the value 6. So the point being is we can multiply together radicals if they have the same index. Next, just as a review from the last section, when we are allowed to have a negative problem, when we can have negatives underneath the square root and get a real solution, that is only possible when you're taking the square root and the index right here is an odd number. Okay, so if that was a cubed root or a fifth root or a seventh root, it has to be an odd number because an odd number index is what will allow you to get multiplied together to get a negative number on the inside. So just a reminder of that, if you get a positive number that's even up there in this spot and you have a negative number inside, then there is no real solution. So let's take a look at our problems here. We have a couple examples just to walk us through. So this first one, we're going to kind of review third and fourth degree roots. Remember, we're going to break this into a perfect cube times what's left over. So here my first bracket is going to be my perfect cube, and then my second bracket is going to be what is left over. So the perfect cube that goes into negative 16, that is negative 8, because negative 2 times negative 2 times negative 2 is negative 8. Does x to the 6, does 6 divide evenly by 3? It does, so all of x to the 6 goes in front. And what's the largest multiple of 3 below y to the 11th? That's y to the 9th. What is our leftovers? A positive 2, no x's, and 2 y's. Well, now we just take the cubed root, giving us our answer of negative 2, divide 6 by 3, so x squared, and divide 9 by 3, y cubed. And then we have the leftover 2y cubed. Make sure when you put that leftover, you clearly put a little 3 in the index as your root. Let's look at an example of a fourth root, fourth index problem. We've got the fourth root of 32, a to the fourth, b to the ninth, c to the 10th. I tried to include all the different possibilities here. So once again, we're going to break this into two roots. The first root will be the perfect powers of 4, and the second root will be what is left over. So if you think about your multiples of 4, 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, and 4 to the 4th is 256. Well, 16 is 2 to the 4th with a leftover of 2, because 2 times 16 is 32. A to the 4th evenly divides by 4, so all that's going to go in the front. B to the 8th evenly divides by 4, leaving you 1b at the back. And c to the 8th evenly divides by 4, leaving you c squared as the leftover portion. Let's try to figure out our answer. The fourth root of 16 is 2. Divide a to the 4th by 4, and you get a. Divide b to the 8th by 4, and you get b squared. Divide c to the 8th by 4, and you get c squared, with your leftover 2bc squared. Remembering once again, you need to put that small index of 4 inside your problem. So that's a little review of third and fourth degree roots or indexes. Let's now look at some examples of multiplying and simplifying. When we're multiplying, we're going to multiply the outside of the radicand together first. And then secondly, we're going to multiply the inside of the radicand together. Then we're going to take that new problem and simplify it. So here we go. 3 times 2 is 6. 7 times 21 is 147. But I'm going to leave that as 7 times 21 because later on that's going to make it easier for us. X cubed times x cubed is x to the 6th. Remember, you add your variables, and y squared. Now we're going to write this as a perfect square times what's left over. Remember, I just brought down my 6 from one line to the next line. It has no impact on the problem other than it just keeps coming down each time. 7 times 21. Well, in the 21, there's another 7. So that gives me a 49 there and a 3 there because we have 7 times 3. X to the 6th is even. Y squared is even. So both of those will go on the front because we're taking the square root here. This leads us to then simplifying this down, and we're going to have that 6 come down just like before. The square root of 49 is 7. Cut x to the 6th in half, x cubed. Cut y squared in half, y, with square root of 3 at the back. We're going to want to multiply the 6 times the 7, so my answer would be 42 x cubed y times the square root of 3. Let's look at B. There's nothing out front of either radicand or either radical sign, so we're just going to multiply our numbers together, realizing we have cubed roots. 25 times 5 is 125. X to the 1st times x to the 4th, we add our exponents and get x to the 5th. Y to the 8th times y to the 3rd, we add our exponents and get y to the 11th. And now we're going to break this into a perfect cube times what is left over. 125, as you remember, is a perfect cube. X cubed is the highest cube underneath x to the 5th with a leftover x squared. And y to the 9th is the highest cube under y to the 11th with y squared left over. So let's take the cube root of 125 and get 5. Divide x cubed by 3 and get x to the 1st. Divide y to the 9th by 3 and get y cubed. And then we have the remaining radical of the cube root of x squared and y squared. Let's try 2 at the bottom. We have a square root here on the bottom left. We have a 3 in front, so that 3 is going to come way out front, and then we're going to combine our radicals. 8 times 40 is 320. Then we have y to the 7th. Now we're going to break this into a perfect square, and what's left over? Remember, you're going to have to bring down that 3 in this case to make it easier and straightforward. And now you have to think, what is a perfect square that goes into 320? Well, the perfect squares under 320 that you might want to start to try is, you could obviously try 4, and 320 divided by 4 is 80. But 80 also divides by 4, and that gets you 20. And 20 also divides by 4, and that gets you 5. So, therefore, you could determine that 64 is a possible divisor of 320, and 64 is a perfect square. So 64 and 5 would be your 2 possibilities with a perfect square and what's left over. Now we looked at the y to the 7th, and we say y to the 6th is the highest even number underneath 7 with 1 left over y. At this point, we've done most of the work, leaving us an answer of 3 times 8, divide y to the 6th by 2, y cubed, root 5y, and that's going to take us to a final answer of 24 y cubed square root of 5y. Knowing your perfect squares and trying those perfect squares is going to make us a lot easier as we go through this. Let's look at example D. We do have both cube roots here, and so it is important to identify the fact that we do both have cube roots in these little spots in our indexes. And so we're going to combine the 2 and the 5 and get 10. Now we're going to combine everything inside. 6 times 4 is 24. X to the 4th times x to the 5th, we add our exponents and get x to the 9th. Y squared times y to the 11th is y to the 13th. Now we're going to remember this is a cubed root of this whole problem. So the 10 is in front, and we have the cubed root. The perfect cubes will be in the front, and then whatever is left over will be at the back. 8 is a perfect cube, left over 3. X to the 9th is a multiple of 3, nothing left over in back. Y to the 12th is a perfect cube because it's a multiple of 3 with a single y left in back. What does that leave us? The 10 comes down. The cubed root of 8 is 2. Divide x to the 9th by 3 and get x cubed. Divide y to the 12th by 3 and get y to the 4th with the cubed root of 3y. Final answer, 20 x cubed y to the 4th times the cubed root of 3y. So, this is just a very quick example of how we multiply radicals together. All we really added is the idea of cubes or fourths in terms of their index. Let's look then and compare this as to how we add and subtract radicals. When we're adding and subtracting radicals, the new idea that we're going to have you focused on is we need to make sure that we have like radicals that we're adding and subtracting. I can't emphasize this enough, this like radicals. It has to have two qualifications, both the same index and the same radicand. If those ideas are true, then and only then you can add them, okay? Only if the radicand is the same, you can add like radicals, okay? So we have to have a lot of things similar in order to be able to add. For example, on our first one over here to the right, we've got 3 root 14, 6 root 14. They both have the same radicand, and they're both square roots. So we're allowed to add them to 9 root 14. Sometimes, if the radicand is not the same, for example, down here, we've got 2 root 12 and root 27. There's times that we're able to break down that root 12 into a 4 and a 3, the 27 into a 9 and a 3. The square root of 4 comes out as a 2, and 2 times 2 is 4. The square root of 9 comes out as a 3 here, which now you have the same radicals, or same the radicands, and you're allowed to add them to get 7 root 3. So let's practice a couple of these. I think you'll find them, they're fairly straightforward. Question 1, are they both square roots? The answer is yes. Question 2, are they both square root of 7? The answer is yes. So you're allowed to add them because they are like radicals. So that would be 5 square roots of 7. For B, notice we have the same radicand and we have the same index, both being 2. So once again, we're allowed to add them, 9 square root of xy. C, notice we have the same index. They both have a root 3. However, the radicand is not the same. One is x and one is 5. So if you were asked to simplify this, you would not be able to simplify it any more than just writing 2 cubed root of x minus 2 cubed root of 5. Or if you needed to say, you could say not possible to simplify any further. But you need to specify that the answer that is written is the answer involved in the problem. So let's practice doing this. We're probably going to have to do some simplification first on these problems. So let's just remembering our square roots and our cube roots and things like that. We have 3 root 20, root 45, and 4 root 80. So let's break each one of these down. Root 20 is 4 and a 5. 45 is 9 and a 5. And 80 is going to be something you would have to assume in a 5. So if you're not sure, divide your calculator. Take 80 divided by 5, and you find it's 16. What a coincidence, it's a perfect square. So we've got 3 times 2, root 5. We've got 3 root 5. And we've got 4 times 4, root 5. Now I'm going to highlight where these parts came from. The 4 comes to the 2, the 9 comes to the 3, and the 16 comes to the 4. This is just a case where being careful with your detail will pay off. 3 times 2 is 6 root 5, minus 3 root 5, plus 16 root 5. 6 minus 3 is 3. 3 plus 16, therefore my answer 19 root 5. Let's take a look at letter B. The square root of 50, 3 squareds of 32, and 5 squareds of 18. 50, as you can likely, breaks down into 25 and 2. So just a key, let's be looking for something and the square root of 2. Well, 16 times 2 is 32. And what times 2 is 18? Well, 9. So now we can identify, it's very nice, we have a perfect square, and a perfect square. That seems to work out nice, so let's make our square roots now. 5 root 2 plus 3 times 4 root 2 minus 5 times 3 root 2. Notice I'm not skipping steps, I'm just showing all my work. So 12 root 2 and 15 root 2. Remember to show your work. It's really going to save you for detail. And these problems involve a lot of detail. 5 plus 12 is 17. 17 minus 15 is 2 root 2. Let's take a look at problem C. I created this problem to help us get an experience with cubed roots. It's a very similar approach. However, they're just cubed roots. So we say what cubed root goes into 16. Hopefully by now you realize that's 8 and 2. As we work through that, next you would have to then assume what cubed root goes into 24, and we're going to have to hope that the leftover is going to be possibly a 2, but we're not sure. What cubed root goes into 24? Well, once again, 8 goes in, but you have a leftover of 3. Interesting. We're going to have to deal with that in a second. Well, let's take a look. 5 times 2 times the cubed root of 2 minus 2 times the cubed root of 3. Well, 5 times 2 is 10, cubed root of 2. 2 times 2 is 4 times the cubed root of 3. Are we allowed to go any further? Well, we have the same index. They both have a 3. However, we do not have the same radicand. One is 2 and one is 3. And so in this case, this is as far as we can go, and this is our simplified answer. Let's look at problem D. 10 fourth root of a perfect root of 4 times what's left over. Well, 81 times 2 is 162, plus the fourth root of a perfect fourth and what's left over. Well, 16 is a perfect power of 4, and with a 2 left over. Don't forget to put your little indexes of 4 on your square on your roots. So we have 10 times 3, fourth root of 2, plus 2, fourth root of 2. That's 30, fourth root of 2, plus 2, fourth root of 2. Now, in comparison to C, we do have the same radicand on these. They both have a radicand of 2 and an index of 4, so we are allowed to add them, giving us 32 times the fourth root of 2. So it's just a case of making sure that both your radicand and your index are the same. Our homework today is going to be 2 small pieces out of 2 different sections, and I've given you those problems down here below to use to work with. I hope this has been helpful in understanding how to multiply and also to add radicals once we simplify them together.